This is almost same like your directivity. So we are plotting the LHCP. We'll plot the horizontal H and see what is the answer. Horizontal polarization. You can see the difference, right? The shape is changing. Vertical. You can see it is a complete circle. It's a proper sphere. And RHCP and LHCP, you can see. And see the directivity is maximum value is 2.32 dBi and the minimum value is minus 259 dBi. So directivity at the frequency 70 megahertz, we are designing. Calculate the beam width. I told you already beam width, single beam width is single angle means 2 times. 2 angles you have been subtracted. So 208, 252. You subtract, you get 44. 288 minus 332. So even if you take the ignoring the sign, you have to take the angle. So the beam width is 44 degrees, which means that the antenna is a very broad antenna. The directivity is very, very larger. It is going to be very, very broad. Whenever we want to have an antenna which is going to be specific to an application, the first thing what you see is directivity. The directivity of an antenna should be very high and the beam width should be very, very less. Because only when the beam width is less, it can target a particular direction. If your beam width is large, then the antenna cannot be used for a particular application. So here the beam width is 44 degrees, which is very, very large for an antenna. So it is highly not recommended to use dipole antennas. If you are using dipole, you have to keep a reflector at the back side so that all the radiations will be sent along the one particular direction. Now we are seeing the impedance. What is the impedance of the antenna? You can see the impedance for the 4 elements. You can see what is the impedance here. Okay. So the impedance is plotted here. Resistance element and reactance element. So reactance is 0 somewhere outside this frequency range. So where it is 0, that is going to be the resonant frequency of the antenna. Okay. So if you type the command 1:4, here you can view all the things of all the 4 elements at a time. Okay. Then finally S parameters. What is the S parameter of the antenna? And you see S parameters are, you have 4 parameters and all the 4 parameters are plotted here. S11. And you have it's a 4 cross 4, it's a 2 cross 2 array, right? So totally you have 4 elements. So naturally your S parameters will have 16 elements. 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. So totally 16 elements you have. And you can see only the plot for the 3. The remaining are all not that much significant. Okay, the remaining plots are not that much significant. Return loss. They are measuring the return loss. You can see the return loss is increasing. Somewhere one point the return loss will become big. That is going to be the resonant frequency of the antenna. Okay, so each element 1 I have plotted. So if you want for element 2, 3, 4, if you type 1, 2, 3, 4, you can plot the return loss for the remaining elements. And charge and current distribution. So how the current distribution is happening? Again, this is done by finite element analysis. So you can see the charge maximum is along the tip of the antenna and minimum is along the center. Whereas if you see the current distribution will be the same because current is proportional to charges, right? So at the center, you will have maximum current. For dipole, at the center, you will have maximum current. At the edges, you will have 0 current. But the same thing is reversed with respect to charge. So at the center, you have minimum charge, and the edges will have maximum charge. So that is going to be the functioning of the antenna. So we are going to calculate the correlation, whether the arrays or whether the incoming signal is correlated between the antennas. So correlation, I told you maximum value is 1, minimum value is -1. So it can vary from -1 to 1. And you can see that maximum correlation is 0.2. Okay, maximum correlation is 0.2, which says that there is almost no correlation between the elements of the array. Now change the visualization. So I am changing the visualization of the array. Now I am having 4 cross 4, 16 elements array. Now you can see the difference. You are having a 4 cross 4 dipole array, which will totally will have 16 elements in the array. And I'm spacing the elements in a non-uniform fashion. See the previous thing, everything is spaced at uniform distance. Now you see they are placed randomly. I'm changing the distance between the antennas. So that is also possible. Once you do all these things, again you can measure all the parameters and you can see whether is there any benefit to derive. You're going to change the different distance between the antenna arrays. Okay, so this is one example we have seen how to model antenna arrays. Okay.